Getting to the moon sounds simple enough. Point a rocket at it, fire the engines, and go. But spaceflight is nothing like that. Every kilogram of fuel costs thousands of dollars. Every inefficiency multiplies across the mission. Every miscalculation can mean the difference between success and silence. Every space mission is, at its core, a fuel management problem. Rockets don't burn their engines for the entire journey. That would be impossibly expensive and impractical. Instead, spacecraft use short, precise burns to set themselves on a trajectory, and then coast the rest of the way, carried by momentum and gravity. And when you're talking about sending humans to the moon, repeatedly, as NASA plans to do through the Artemis program, those savings are not just financial, they are strategic. More efficient routes mean more payload capacity, more scientific equipment, more supplies, more capability for the crews that will one day live and work on the lunar surface. The gravitational pull of every planet, moon, and star creates natural pathways through space, routes where spacecraft can travel long distances using little or no fuel, carried along by the invisible architecture of gravitational forces. Scientists call this the interplanetary transportation network. Think of it as a hidden highway system, stretching across the entire solar system, built not from concrete and steel but from physics itself. Between Earth and the Moon, these gravitational pathways are called variates, natural trajectories shaped by the combined gravitational pull of both worlds. For years, scientists assumed the most efficient approach was to enter the lunar orbit from the side closest to Earth. It seemed logical. It seemed obvious. After all, why travel further than you need to? But logic, it turns out, is not always the same as optimal. An international team of researchers led by Alan Kardec de Almeida Jr. at the University of Coimbra in Portugal, alongside colleagues at the University of São Paulo in Brazil, set out to systematically test every assumption about the cheapest route to the moon. And buried deep inside those simulations, they found it, a hidden route, one that approached the lunar variate not from the near side as everyone assumed, but from the opposite side entirely. But fuel efficiency is not the only advantage this hidden route offers. There is a second benefit, one with direct implications for crew safety on future missions. When the Artemis II astronauts completed their historic journey around the moon in April 2026, there was a moment of silence, not of reverence, but of necessity. The spacecraft passed directly behind the moon, cutting off all communication with Earth. For that period, the crew was entirely on their own. The researchers are clear that this discovery is a beginning, not an ending. Their current model accounts for the gravitational influence of two bodies, Earth and the Moon. But the solar system is far more complex than that. The Sun's gravity, Jupiter's enormous gravitational influence, the subtle tugs of dozens of other bodies across the inner solar system. Incorporating all of these variables into future simulations could reveal even more efficient routes, trajectories that use less fuel, take less time, or open up entirely new options for mission planning that nobody has yet imagined. Space travel has always been about solving problems that have never been solved before, finding paths through environments where no road exists, using physics as the map and mathematics as the compass. The universe is full of hidden routes. We are only just learning how to find them. The most efficient path was never the obvious one. It never is.